other public key crypto systems. So RSA is not the only one for public key, although RSA is most prevalent, most commonly used method for two reasons. One, it was very simple, and second, they found a company which really showed how to use it anyway. Other people were not so business minded. So we'll talk about first Diffie-Hellman, then Algmal, and then elliptic curve. So the Diffie-Hellman, remember, these are the guys, two professors at Stanford, who invented public key, right? And so they came up with a method so that you could exchange the keys in public. So suppose I want to share a secret with somebody at that corner of the room. The only way I can communicate with them is by talking to them just in the open air. How can I tell them a secret word that nobody else can understand? Right? So they came up with that method. Allows two parties to agree on a secret key using a public channel. And so the way it works is that A, this is the first party, and B is the other party. A selects a large prime Q and then selects alpha, which is a primitive root of Q. Some of you remember the primitive roots. We talked about primitive roots of 19. So Q is a prime and then alpha is a primitive root. All right? And then it selects XA as well. So three things it selects: XA, alpha, and Q. Then it computes YA equal to alpha raised to XA mod Q. It computes this thing. And it sends on the public channel A, Q, and YA. Everybody can hear A, Q, and YA, and B can hear that too. B hears A, Q, and YA, then B selects another random number, XB, and then raises alpha to XB mod Q, calculates by B. Alpha is there, Q is there, and XB is selected. It sends by B to X, to A. Alright? Now, what A does is, when it gets by B, it raises it to power XA because it knows XA. Right? It didn't make it public. Nobody knows XA, but A knows it. It can raise it to that power and it calculates YAB, which is basically alpha raised to XA XB mod Q. Because you see, YA was alpha raised to XA and then YB was YA raised to XB. So basically YAB is alpha raised to XA XB mod Q. And so this guy can calculate very easily. And B does the same thing. It calculates YAB equal to YA, which was received on the public channel, and raises it to power XB, the number that is selected, and then it knows YAB. So now both of these guys know YAB, but nobody in the middle can calculate YAB. Okay? Why they can't calculate YAB? Because they cannot factor, they cannot do this is a large number Q, they cannot factor it, they cannot do discrete log and things like that. So even though everybody knows that YA is alpha raised to some power, not Q, they can't calculate XA. Okay? So because the discrete log is very difficult to compute, that's why this thing works. Any questions? So, this is one way you could exchange the talk to stuff. For example, in the Wi-Fi, when you talk to the access point, you could get a key that only you and the access point have it, nobody else has. So example of Diffie-Hellman would be alpha equal to 5, Q equal to 19. Obviously, you will not use such a small number. But since we have already used 19 as a prime number before, and we know it's all these primitive roots, we know that 5 is one of its primitive roots. So we select 5, 19, and then A selects 6, just randomly selects XA. 6 as XA. Then it sends alpha raised to 6 mod 19, which comes out to be 7. So it sends 3 numbers, alpha, Q, and YA. Alpha is 5, Q is 19, and YA is 7. Yeah, any question? No. Okay. It sends that. Now B selects another random number, just randomly it selects 7 as its number, and then it sends 5 raised to alpha raised to YB. This is YB is 7. Alpha raised to YB mod 19, 16. It sends 16 on the channel. So on the public channel, you have 5, 19, 7, and 16. Now A computes this 16 raised to its number. If you go back again, you see step by step they are following. A computes YB times raised to XA. Whatever number is coming, it raises it to number that it has selected earlier. So it just raises to the power 6 and computes 7. So that is the secret. And B does the same thing. It takes the whatever had come earlier and raises it to power XA, the number it has selected, and it also comes up with 7. Obviously, both of them have to come with the same number. And that is the secret. And this is not a good example for another reason, because 19 is not a good choice for prime numbers. If you have a prime number where Q minus 1 upon 2 is also a prime, in this case Q minus 1 is 18, by 2 is 9, it's not a prime. If that was the case where that was also a prime, that would be a better prime, and that is called a safe prime. If it is not a safe prime, then breaking it is easier than safe prime. See, the thing is, because now this is a number which is not a prime, now you start with the factorization of this, and somehow from here you can get to the factorization of the other thing. Because if this is a prime, and this is not as big, this is only half as big, which means 1 bit less than Q, right? And if it is a prime, then it is equally difficult to factor. I mean, of course, you're not going to be able to factor it, and so you won't be able to get that. But if you have a factor, then it could be very small number of bits. So, for example, 3 would have half as many bits as 9 or 17 or whatever, right? So, okay. All right. Now, Diffie-Hellman is actually, while it allows you to provide the secrecy, it doesn't allow authentication. So remember, when we talked about public key encryption, we said, you put the first lock and you put the second lock and you put the third, basically you can decrypt it so that it provided both the authentication and secrecy. So nobody could read it, but only you could read it, and you could be guaranteed that it was sent by the other guy, right? That Diffie-Hellman doesn't do it. So let's see how it can be attacked. So Alice sent a number to Bob, but Dot on the way catches that number and sends another number to Bob. Right? Similarly, Bob sends an answer based upon this number. Dot catches it and sends another number to Alice. So everybody is happy, but Dot in the middle now has the secret which it shares with both of them. And yeah. What is implemented? Yeah, the man in the middle attack basically is as old as the Diffie-Hellman exchange. Basically, as soon as you publish, people, maybe Diffie-Hellman himself themselves said, look, this is for secrecy, not for authentication. So somebody else can come in the middle. So yes, your question is that implemented means, if they are going to implement Diffie-Hellman, before that they will do authentication. They want to make sure that Bob is talking to Alice and not to somebody else. Okay? All right. So basically, the idea is that it does not provide authentication. You should know that. And So you can use RSA authentication or other alternatives. Then Al-Gamal, he has a very similar method, which is related to DH, which is Diffie-Hellman, and he uses Galois fields, finite Galois fields that we saw a minute ago. I mean, not a minute ago, a few chapters ago, and then it is again based upon discrete logarithm. So this is somewhere halfway between Diffie-Hellman and RSA. So here, A selects XA, alpha, and Q, just like Diffie-Hellmans do. And it calculates XA, YA is equal to alpha raised to XA mod Q and sends out exactly like Diffie-Hellman, alpha, Q, and YA. The second guy selects a random key K, which is like XD, and very much like Diffie-Hellman calculates capital K. But instead of sending out capital K, it sends out C1, which is alpha raised to K mod Q, and C2, which is K times M, where M is the message. It sends out C1 and C2. Okay, M is the message that it wants to send. So what will happen is when A gets the C1 and C2, it can calculate K, just like Diffie-Hellman, and then it can calculate M, the message itself. So now what has happened is not only they have been able to, this is one step ahead in the sense that not only they have been able to share a secret, but they have been able to exchange a message in the same two messages. With just two messages, they have been able to send a message M. So in Diffie-Hellman, you would have gotten the secret done, and then you would have done the messages, one after another. So this is like that, right? However, K must be unique. Each time you use this thing, you start with a new K, and then you get a new C1 and C2. But every time you use the same key, you are giving more data to the hacker. And so we will see this throughout this rest of this chapter, rest of this course, that we change keys very often. Okay, so to summarize Al-Gamal, it is very similar to Diffie-Hellman, and very similar to Diffie-Hellman, they send alpha Q YA, but instead of sending YB back, C1 alone, they also send a message. So encrypted message which can be decrypted at the other end right away. Yeah. Here it says, as shown here, K must be unique each time. So here you would change K for each message. So this guy will select a new key every time, and this guy doesn't have to worry about it. Actually, to be fair, the key is not really changed fully because this part of the key remains the same. Right? Yeah, so this K is being changed. Now, to be correct, what you will do is you will, every time you change a message, you want to send a message, you will start from the beginning. And then you will change all of these plus K.